Okay, I'm going to cover some advanced topics on the compiler. Um, so, so on the back end, it has a type, register, and a displacement. The displacement is sometimes an immediate. Anyway, I wanted to okay, so an intermediate code has internal or the intermediate code type. What is this? Precedence? I don't know what this is. This is the count of when it's converting to machine code. This is the count of machine code bytes. The advanced topics include how it deals with floating point and figuring out the expression type during pass 0, 1, 2. Anyway, so first I want to talk about register variables. So there are 16 registers in a 64-bit machine. So I said in the last video that AX, BX, CX, and DX can be clobbered by each intermediate code. Each intermediate code is absolutely free to clobber AX, CX, DX, BX. Sometimes the incoming argument is in RAX. So I use two. Okay, so it starts as a stack machine, but it converts to a more conventional calculation. When you're doing a stack machine, you can use registers to be deeper in the stack. RAX is like the top of the stack, and then R8, R9 are like lower, or I don't know, what do you want to call it, higher or lower? Anyway, now it uses RSI, RDI, R10, 11, 14, 15 for register variables. However, R12 and R13, because they're alias, or I don't know what you want to call it, not alias, but they're similar to RBP and I guess RSP. They're the anyway. They don't do some of the modes. They require an extra byte for some of the addressing modes. So what I do is I separate my register variables into pointers and non-pointers. And anyway, so remember, RAX is like the top of the stack. It links together different intermediate codes. R8, R9 are like, they're actually temporaries. In other words, they're not even preserved. So if you're doing an all assembly function, you can clobber AX, CX, DX, BX. You don't have to save those. And you can clobber 8 and 9. So these are stored in a mask. So you could change this if you wanted to make 3 temporaries. You could do something. Anyway, now I tried to get tricky and alternate R8 and R9 so that some when you're doing a call, you have to say, well, anyway, I tried to get tricky and sometimes use R8 and sometimes use R9. Anyway, so it's actually easier doing a 64-bit compiler because you have 16 registers to work with. I don't very aggressively optimize. I don't use my registers very efficiently, but I don't know if it matters. The truth is, all that matters is cache misses. Pretty much all this stuff gets pipelined by the CPU. The CPU can make bad code run just as fast. You don't even need to convert to CISC. You can just do RISC. Anyway, so let's talk about, I guess we can talk about the floating. That's one of the most complicated aspects, is the floating point. There's miscellaneous. When you make a label, it has to keep track of the label, and it has to keep track of jump table code, and so here's an intermediate code. It has a code. It has flags, and it has that one data item. Each intermediate code has one primary data item. Then it has a class, and then this is where it gets ugly. Sometimes it changes the class, and sometimes it needs the original, the line number in the file, and then arguments. In my first version, I had three arguments to do the question mark colon operator, but now I got rid of the question mark colon, so I don't support that, and I have two arguments. Then here's each of these intermediate codes converts to machine code, and it stores the machine code temporarily and then splices them all together for the final output. And I don't make a symbol tree. I make a stack machine, and during my 0, 1, 2 pass, I have to, if you multiply a float by an integer, it has to set the type to it has to convert to a float. Anyway, so during pass 0, 1, 2, I have to build the abstract symbol tree backward, so I almost don't accomplish anything. In other words, I still have to build an abstract symbol tree. I just do it backward. I store the tree argument and the tree class. Anyway, so I have to build the tree in order to resolve the types. Now, here's one of the fundamental issues is let's see. So we start with RISC, and then we convert to CISC. By the end of this, we're doing a anyway. There's there are two arguments to each of these intermediate codes, and sometimes you need to. Sometimes, in theory, they can be on the stack and not in register variables, but it turns out you almost never have stack variables because there's so many registers. So if you have stack variables, then it matters the order of operations. But if you have register variables, you can if you have just register variables, you can reorder stuff and it doesn't matter much. But if you have stack, then pushing and popping makes a difference if you reorder. So one of the fundamental there's a bit that lets you flip between argument 1 first and then argument 2, or argument 2 first and then argument 1. So one of the most complicating factors is in the back end. When you're doing the back end, you have to deal with this A1 first bit. sometimes it reverses it so that you have to do argument 2 first. This the reason this matters is for when you're pushing onto the system stack. That's only if you run out of register variables. Anyway, so you'll see that it used to be a nightmare when I had 3 arguments. That's why I got rid of 3 arguments. I got rid of 3 arguments, and it's a lot cleaner. I don't like the question mark colon operator very much. Anyway, the other thing you'll notice is there's something called a actual address. What is that called? Now, when you're doing something like this, let me see if I can find an example. Okay. Now, I started without register variables. And when you don't have register variables, then this plus plus applies to you pass an address to this plus plus. But if so, you have an address that you're dealing with. Now, if it's a register variable and you hit this plus plus, then it's no longer an address. It's a register variable. So one of the when I added register variables, then I had to check if I was dealing with an address or I was dealing with a register. And so in all of this code, you'll notice that A1 first flag, and then the other thing you'll notice is not address. If it's a register variable, it's not an address. Now, just remember, if it's a register variable, it's not an address. If it's an address, then it's anyway. So almost you have to do a 4-way split. You have to do not address argument 1 first, not address argument 2 first, address argument 1 first, and address argument 2 first. Okay, so that's what you'll see. Now the other issue is floating point. This is really complicated. In the past 0, 1, 2, it figures out the type. So if you have to promote it from an integer to a float, then it sets a flag saying. So this simplifies immediate. It simplifies constants, and it also fixes up. It also starts setting type. No, does that where it does it? It has to. The way I handle floats is the way I handle floats is I'll set a flag saying convert the result to integer or convert argument 1 to double. So for each of these intermediate codes, I can either convert argument 1 to integer or convert argument 1 to double, convert argument 2 to integer, convert argument 2 to double, convert the result to integer or convert the result to double. So there's a flag, and on the back end, on the very last pass, it when it leading into it deals with conversion flags on before handling the intermediate codes, and I think it does it after the end. I don't remember. At the bottom, it should convert the result. So it sets a flag. So result to integer. Now there's one more thing, which is sometimes you have an expression which doesn't have a where the value is not used. Like for example, let's say I plus plus. I equals 0. Okay. Now it's a register variable, so it's not an address, and this minus dependent. This is minus dependency. In other words, when we parsed this expression I plus plus, it could have been j equals I plus plus. If there's not a dependency, then we don't have to, if there's not a dependency, then we don't have to do the final step. So now the floats, I don't even know if I can explain the floats. They're so messed up. Okay, so there's a floating point stack, right? You know there's a floating point stack. Now, between intermediate codes, actually there's 4 different, I think there's even more. For one intermediate code, you can have a float operation on the argument 1, float operation on argument 2, a float operation as the main argument, and a float operation on the result. Each intermediate code can have those 4 different floats. And what I tried to do is keep them on this floating point stack. So in between operations, I either say I start linking together the operations by using the floating point stack. So some of these, this is a don't push for various operations. This is a don't pop. There's one that's don't push, don't pop. I think that's at the bottom. Don't push, don't pop. Don't push, don't pop. So these are templates. This is just some. The compiler assembles this code and then copies it into the output if we're using the floating point stack. So what else is there? So in the expression parser, I generate a warning if you don't need parentheses. That's kind of ridiculous, but it's important to keep on your toes, knowing that I have a different precedence than standard C. Anyway, so in this, it actually makes it quite a bit more complicated. Keeping track of parenthesis warnings. This is the expression parser, which checks. This is where it resolves operator precedence and stuff. Anyway, so the expression parser also handles modifiers and array indexing. Each term can have arrays and stuff. Where there's unary modifier. So you have there's a state machine for the main. This is the state machine here. It checks if you want to follow the logic. It does a unary term, and if a unary term has modifiers like a member of a class, actually, if you take a pointer versus if you have a dot, it's one thing. If you have a minus greater, that's a different thing. Anyway, then after each term, it checks for binary operators, and when it's figuring out precedence, it has to unload higher precedence. Anyway, so the call, somewhere in here, it figures out its function calls. So, I know what I was going to say. I'm sorry if I'm out of order. So when it's doing a statement, if it sees a string as the start of a statement, then it does a function call for standard out. So a string generates a standard out. Character constants generate put char. So I have a feature of my operating system, of my compiler, where normally a character constant is just one letter, but I allow multiple letters, and this is something I learned at Ticketmaster. They deal with characters, or they deal with ASCII. Sometimes you have a 4-byte signature, maybe. Anyway, these are not zero terminated. Anyway, so I went ahead and in my compiler you can do multi-byte characters. This is not UTF. I'm not doing UTF. Screw that. Now there's one other thing I was going to say. When we're at the back end, when we're in the back end of the compiler, here's a rule. If anything gets loaded into a register, it has been promoted to 64 bits. And all intermediate operations are on 64 bits. So this creates some interesting issues. So anything that gets put in a register, let's say U16I equals, this is look at that. We got, let's do 0x. So we got a, this is, I do not obey the rules on smaller integers. That's just how this language is defined. The rule is anything that finds its way into a register is 64 bits. Okay, so this, some people, anyway, it makes, my compiler is 20,000 lines of code, including an assembler and an unassembler. I think that's pretty impressive. I cut some corners, but I don't see that last thing as a problem. Anyway, so how about that?